So, welcome to lesson 21 of the course Industrial Automation and Control. In this lesson, we are going to learn a structured design approach to sequence control. So far, we have mainly seen the programming constructs, have seen small program segments, timers, counters. In this lesson, for the first time, we will see that given a practical problem, how to study the problem, what are the steps that you go through to finally arrive at an RLL program. So, and this will be followed using a very systematic approach, because as I have already told you that industrial control applications are very critical in the sense that if you have programming errors in them, they can be very expensive in terms of money, or in terms of even can cost human lives, etc. So, it is always good to have a very systematic design process by which you can decompose a problem and then finally arrive at a solution. So, we will look at the instruction objectives. The instruction objectives of this lesson are firstly to be able to model simple sequence control applications using state machines. State machine is actually a formal method, and we advocate the use of formal methods because English can be very ambiguous, sometimes contradictory also. So, we have to model it using methods which are unambiguous, consistent, do not contain contradictions, and are also easy to understand and develop. Then from these formal models, we have to develop RLL programs for such applications, and for doing this there are certain, apart from the RLL programs, there are some modern programming constructs which are being made available. One of them is the SFC, or the sequential function chart. So, we will take a look at that and also understand some of its advantages. So, that is these are the instructional objectives of this lesson. So, now let us go through the steps in basic broad steps in sequence control design. So, first step is to study the system behavior. This is a very critical step, and most of the errors that happen in any programming exercise, not only this kind of industrial automation programming, any programming, mainly arises from the fact that the programmer or the developer did not understand the system well. So, this is a very important step, and one must first of all identify inputs to the system, that is the programmable controller program, what inputs it will take. Inputs can come from either from sensors in the field, or it comes from operator interface, which I call the MMI, or the man machine interface. So, somebody presses a push button, that's an operator input, right. On the other hand, some limit switch is made, that is a sensor input. Similarly, identify the outputs. So, switch on motor. So, motor is an actuator, that is a kind of output. There is another kind of output, for example, switch on some indicator or some lamp, that would be an output which again goes to the MMI, or the man machine interface. So, we have to first identify these. Then study the sequence of actions and events under the various operational modes. This is the main task. You have to very carefully understand what is going to happen and what will happen after what, at what time intervals, etc. Then one thing that must be very clearly remembered is that when you are developing an industrial automation program, one not only has to design for normal behavior, but one must to some extent at least take into account the possible failures that can occur. Otherwise, a system that behaves well under normal behavior can behave in a very nasty manner if some simple element of the system like a sensor fails, right. Then even apart from the automated behavior, one has to examine the requirements that exist for number one, manual control. Manual control is very important, because for finally if the automation equipment fails, it should be able to operate the system using manual control, right, maybe right on the field, while the automated control may be actually working quite a distance away from the actual equipment. It may be housed in some control room. On the other hand, the manual controls may be near the equipment at the field. So, the possibility of including such manual controls must be examined. Whether some additional sensors are required, some sensors may be there, but to achieve a kind of functionality some other sensors may be needed. Indicators, alarms, and as well as operational efficiency or safety. These are the factors which must be considered to finally arrive at the functionality. One must always remember that the customer may not always be able to express his or her needs, and a good automation engineer should be able to supplement it with his own experience in such cases. So, having done that, the next step is to convert. Generally these things are captured manually and using a linguistic description, something like something like English statement. So you talk to customers, talk to engineers on the field and get their requirements. But this is very dangerous to use for program development. So we have to convert this linguistic description into formal process models, and in fact a lot of inconsistencies which are there, ambiguities which are there in the linguistic description actually surface at this time. Even for during the process of transforming it into a formal process model, one may initially use intermediate forms like like flow charts, for example. Okay, then finally it is prescribed that one should be able to convert it to a formal mathematical framework, something like let us say a finite state machine, which we will be using here. After up to this the operations are manual. Having done that, then one has to go for design of the sequence control logic based on the formal model, and then finally one has to implement the control logic in the form of an RLL program. And it is preferable that these steps, especially the step D, is made as much as possible automatic, because this is a step which can be done in an automated manner once B and C have been carried out, and for large programs it is always preferable to go for automated programming, because that will always lead to error free programs provided your specifications were correct. So we come back to our old stamping process example which we have seen in earlier lectures. So here is a stamping process, we know this process, so we have made some addition to its functionality to be able to explain certain features of a system and make it more complete. So basic principle is the same, that there is a piston and there are two solenoids, hydraulically driven piston which goes up and down and makes stampings. Okay. So if we now try to write its list of actions, try to create a linguistic description of the process operation, it will look something like this. So in step A, it says that if the auto push button is pressed, so that is an operator input, it turns powers and lights on. So there is possibly a switch, one or more switches, but we will consider it to be one, which will turn the power and the light on the moment the auto button is pressed. When a part is detected, the thing to be stamped, when it is detected, when it is placed at the proper place and detected, so there has to be a part sensor. The press ram, the thing that will, the heavy piece which will move and make a stamping, it advances down and it will stop once it makes the bottom limit switch. So that is again a sensor, and you must have actuators to make the ram move down. Then the press then retracts up to the top limit switch and stops. So it makes a stamping and stops. All right. On the other hand, due to some reason, the operator may like to abort a stamping operation. So there is a stop push button provided to the operator, and a stop push button stops the press only when it is going down. When it is going up, it has no effect, because anyway that is not going to cause any problem. If the stop push button has been pressed, it means that something abnormal might have happened. So the reset push button must be pressed before the auto push button can be pressed for the next cycle of operation. So once you have pressed stop, you have to press reset. It's a kind of acknowledgement that the emergency has gone away and the automated operation can resume. Finally, after retracting after retracting and then going up, the press waits till the part is removed and the next part is detected. So, till the part will be removed, and then after that when the next part will be detected, again the RAM will start coming down. So, this is the English behavior of the system. Okay. So, now let us try to convert it to an unambiguous mathematical description. So, first step, as I said, is to get the process inputs and outputs. So, what are the process? So, here are the process inputs and outputs. So, as inputs we have part sensors, which gives which generates two kinds of events. One is part placed, another is part removed. Then there are three kinds of push button: the auto push button, the stop push button, and the reset push button. These three are operator inputs. Then there are the two limit switch sensors, bottom limit switch and top limit switch. For outputs, we have four outputs. We have an up solenoid which moves the RAM up. We have a down solenoid which moves it down. We have the power light switch, and we have a part holder which holds the parts while it is being stamped. So, these are our outputs. Now, we develop a state machine. So, let us try to interpret this diagram. So, what is happening in this diagram is that let me select my pen. So, what is happening is that you see these squares are the states. We are possibly familiar with state machines. So, a state machine is like a graph which consists of a set of states. These squares are the states, and a set of transitions. For example, this is a transition. This is not a good color. Go back to white. So, this is a transition and this is a state. So, this is a transition and this is a state. So, what the system does is that the system actually during its life cycle or during its activity, the system actually moves from states to states through transitions. So, it actually spends time, most of the time, in the states, and transitions are generally assumed to be momentary. That is, it is assumed that insignificant amount of time is required to change states. So, you see that it says that initially when you have double square, it means that is the initial state. So, if the auto push button is pressed, this is a transition A which gets activated, which will take place and take the system from state 1 to state 2 if the auto push button is pressed. So, this is the transition condition. You can have much more complicated conditions. In this case, we have very simple conditions. And then if this transition occurs, then this system comes to state 2. In state 2, again, if this transition B takes place, whose condition is part placed, it will come to state 3. So, in this way, depending on how the sensors are bringing in signals from the field, the various transitions will be enabled and the system will hop from state to state. That is the behavior of the system. On the other hand, these green rectangles indicate that at each state, which are the outputs which are on. For example, you can see that in state 1 nothing is on, none of the outputs are exercised, while in state 2 the power and lights are on. In state 3 the down solenoid is on. Actually, this is the state when the solenoid is coming down. So, you see that this is the initial state. Here the system is switching on the power and the light and possibly waiting for part place signal to come. So, it might spend some time here. Then it is coming down, so it takes time there. Then from here it could either go this way or go this way, and depending on which one of this have come. So, it may so happen that the bottom limit switch, if the stop push button has not been pressed, then eventually it will the bottom limit switch signal will come, and then it will come to step 4, in which it will activate these outputs. On the other hand, if before the bottom limit switch is pressed, if the stop push button is pressed, then it will come to this state where it will simply stop and put the power and light off. So, you see, so this is the way, using a graph of nodes and edges, we can describe the behavior of the system unambiguously. So, now, so this is what we know, what we call the state transition diagram, and these are the outputs which are exercised at different and that is actually also in captured in what is known as an output table. So, the output table says that among the four outputs that we have, namely power, light, part hold, power light switch, part hold, up solenoid and down solenoid, which are, what are their status, whether they are on or off in the various states. So, there are 6 states and there are 4 outputs. So, it says that the power light switch stays on in state 2, 3, 4 and 6, right, while the part hold stays on only during 3 and 4, up solenoid is 1 during 4 and down solenoid is 1 during 3. Having done that, we can start developing our, so you see, we have seen that as the system moves on, the various state logics and transition logics are alternately computed. So, first there is a state in which some state logic will be satisfied, depending on that outputs will be exercised. After that, at some time some transition logic will get satisfied. So, now the system will come to a different state. So, the previous state logic is going to be falsified and the new state logic will now become true, and then based on that the corresponding outputs will get exercised. So, this we have to now capture in a relay ladder logic program, right. So, we will organize our program into 3 different blocks. The first block, the first block will contain, so maybe I will choose this pen now. So, the relay ladder logic will consist of 3 different blocks. Okay. The first block will contain the transitions. This is multiple rungs. Then the state block and finally the output block. So, we will now describe these 3 blocks in the case of this example. So, let us first see the transition logic. For example, what does it say? It says that when will transition A logic will be satisfied? The transition A logic, if you recall, brings the system from state 1 to state 2. So, if you wanted to see that, we could go back just for once. So, you see here, transition A takes the system from state 1 to state 2, transition B takes it from state 2 to state 3, transition C and D are in parallel, it could take state 3 to either 4 or 5. So, let us remember this and then go ahead. So, it says that if the system is in state 1, if it is in state 1, that depends on the state logic, then the corresponding to every transition we have an output coil, and corresponding to every state we have output coils. So, this is actually an auxiliary contact corresponding to the output coil called state 1. So, it is an abstract variable actually. So, it says that if the system is in state 1, then this contact will be made, and at that point of time, if the auto push button signal comes, then transition A will get enabled. So, it will be on, right. So, if we have modeled our system well, then at a time only one transition will get on, right. If we do not consider concurrency, then at a time only one transition will get on. Now what will happen? Now in the next stage, So now transition A becomes on and state 1 was already on. So at this point of time we come to the state logic. So now let us see what happens in the state logic. In the state logic, see, state 1 was on, right. Now because state 1 was on and because auto push button was pressed, transition A became on. So the computation came from the transition logic to the state logic. So what happens is that it found state 1 is on. So what happened is that it found that the transition A is on. At this point of time it found this transition on, because transition logic has been already evaluated and it has been found to be true. So therefore this auxiliary contact will be closed. So therefore now state 2 will be on. Now once state 2 is on, two things happen. Firstly, you see in the next, because state 2 is on, this will be on, this contact will be on, and this contact will now be off. So in the next cycle, in the next scan cycle, when these rungs will be evaluated, this will go off, and because and transition A will, because see this will go off and this will go off, therefore because transition A will go off, so therefore state 2 this can go off, it does not matter because this is on, so therefore this will stay on. So therefore it says that now the system is in state 2, right. Now when in this way again, when state 2 is on, at that time in the next cycle some other transition will become enabled depending on what sensors, what sensor signals are coming. So similarly it will turn out, for example in state 3, now at some time transition B will take place. Transition B means that transition B is, let us see transition B. So transition B is part placed, correct. So when the part will be placed, then if that part placed signal comes, then what will happen is the transition B will be on and these are not yet enabled, so therefore state 3 will be on, right. On the other hand, while state 3 is on, if either transition C or transition D occurs, transition D is due to the stop push button being pressed and transition C is due to the bottom limit switch being made. If any one of these occurs, then it will no longer be in state 3, but it will go to either transition state 4. If transition C occurs, state 3 will be falsified and state 4 will become on. On the other hand, if transition D occurs, then this will be falsified and state 5, which is not shown here, will become on. So you see that mechanically, once we have developed the state graph, we can simply mechanically describe its behavior. So corresponding to every transition we are going to have one rung, corresponding to every state we are going to have one rung, and as I have described, we are going to put the enabling logics. So we are going to say just from the graph that if when the system is at state 1, if auto push button is pressed, it will go to state 2. Simple, this logic which is given from the graph will take every transition and will write the corresponding logic in the transition logic. Similarly, we will say that if transition X has been enabled, then it will reach this state. So we can do it from the graph mechanically, just one by one. This writing can be actually written by a program itself. So one need not really think too much about the logic. One should think about the logic while he is drawing the diagram. After that, the programming becomes automated. This is very useful. Okay. So now next we will have the output coil, output logic. Output logic is very simple, very simple, especially in this case. So the output logic says that if you are in state 2, then power light switch should be on, as we have given in our output table. So only thing is that look here that we have also added some manual switch. You know, it can be sometimes we may need to check, we may need to do things manually also. So, the power light switch will be on, here we have put a manual switch. So, if the PLC is running, then if we press the manual switch, then also power light switch may be made on. Similarly, we can have a manual down push button. So, we can, this is just to demonstrate that you can put additional logic to include manual operation of the system. So, in this, so otherwise this program simply says that while you are in state 3, down solenoid will have to be activated, very simple. Compare this with the kind of programs that we had written earlier. In fact, for this process itself we had written some programs. So, there we did not have any concept of states and transitions, we were directly trying to write outputs in the form of inputs. Now, the problem with this kind of problems is that they are here systems generally have memory, that is why you need the concept of states. It is not that if you get a certain kind of inputs, you will have to produce certain kinds of outputs. It depends on which state the system is in. So, the concept of state is very important, and well, you can bring it down bring it possibly in certain cases using some temporary variables, but the kind of here you see if you look at this program says it is very complicated logic, and I am not even 100% sure, it is very difficult to be 100% sure whether this logic is foolproof. It says that if the auto mode, by the way, this auto mode is actually a it's an auxiliary contact corresponding to some logical variable which you can set by a simple run, that if it is auto PB and then you have an auto mode coil and then you have this is auto PB and here you can have auto mode. So, you can have a auto mode coil and this will be an auto mode auxiliary switch, so that the PB can be released. So, this is a sort of a persistent input. So, if this auto mode is on, so it says that this everything will work only if the auto mode is on, and then if the bottom limit switch is made and the down solenoid is not on, then the up solenoid will be energized. Similarly, and once the up solenoid is energized, it will remain energized until the top limit switch is looks okay, but one is never sure, and especially when problems will have 200 states, then it will be impossible to write such direct programs. Chances will be very high that if somebody wants to write it, he will make mistakes. So, this is a typical example of unstructured programming, the kind of things that we did before this lesson. Now, having said these things, so this is in very brief, this is a structured design approach to RLL programming. Now, we must mention, since we are coming to the end of this programming part, we must mention that there are certain standards of programming languages which have come. For example, IEC 1131, IEC stands for the International Electrotechnical Commission, and the 1131 is a number. So, this is an international standard for PLC programming, and it classifies languages into two types. One are graphical languages, things like functional block diagrams or ladder diagrams. These are graphical languages. On the other hand, there may be several text based languages, for example, structured text or instruction list. These are some of the kinds of programming paradigms. I already told that although we are learning about the RLL, there are several other programming paradigms which are also supported by various manufacturers, and these are typical examples of them. So, for now we have understood that this state based design is very useful. So, therefore, to be able to capture this state transition logic, a separate language has been proposed, separate methods of programming, advanced programming have been proposed, and we are going to take a brief look at that. So, some of the merits of this kind of advanced programming which takes this kind of abstract state transition logic, firstly because they have open standards, in the sense that anybody can write a program which can be used by somebody else. Then structuring of programs in terms of module helps in program development and program maintenance, very important. Program upgradation, you want to add a new functionality, you will find that it's very simple. Just change the state diagram and then find out that now in the new state diagram, if you have 3 extra states, simply you have to add those corresponding rungs. If you have some extra transitions, you have to add those rungs, and if you have to redirect some transitions to now new states, then you have to code that logic, that is that transition should now come in that state logic. So, you absolutely know that which are the places where you have to make change. These are the very standard benefits of structured programming. Then it is not necessary that all the times every rung has to be computed. In fact, only a few rungs are actually active and the other rungs are inactive. So, there is no point, you can save lot of computational time by skipping those. So this needs to be done, that will improve computational performance, and it supports concurrency. That is very important, that it supports concurrency, because it very often happens that there are many things, several things which will be taking place together, and which are best modeled as concurrent, and especially now that we have these so called multitasking operating systems or executives running on microprocessors. So there is no reason why this cannot be done. I mean, we have the technology to enable it. So therefore we must use it. So therefore we have a formalism which is standard and which are called sequential function charts. So a sequential function chart is actually a graphical paradigm for describing modular concurrent control program structure. So remember that it is basically used to describe structure and not the program itself. So which part, so as if you have organized your program into a number of well written functions which are modularly arranged. So you just using the sequential function chart, you are just describing that which of these functions will be executed when and under what condition. So you have this remark which says that the SFC merely describes the structural organization of the program modules, while the actual program statements in the modules still have to be written, probably using existing PLC programming languages, something like either RLL or instruction list or whatever. So if let us quick look at the basic SFC constructs. They are basically state machine like constructs and contain some constructs which are simple programming constructs with which we are familiar. So you have basically just like states and transitions, here you have steps and transitions. So each step is actually a control program module which may be programmed in RLL or any other language. So as I said, it's a function. Similarly, the steps can be of two types. Number one, initial step, I had marked the initial step, and the initial step execution can be of two types. One is when the first time you are executing after power on, and second is if a program reset, actually sequential function charts have some standard instructions which will reset, which are assumed to reset the program. So after reset also you can execute a particular type of step called the initial step, typically used for initializing variables and states and intermediate variables. Otherwise you have regular steps, which one of them are active at any time actually depends on the transition logic, as we have seen. So when a step becomes inactive, its state is initialized, and only active steps are evaluated during the scan. That saves time. Now we have transitions. So in transition, each transition is also a control program module which evaluates based on available signals, operator inputs, etc., which transition conditions are getting enabled. So once a transition variable evaluates it true, then the steps following it are activated. And we say steps because in this formalism typically we have seen that one transition can go to only one step, provided you do not have concurrency, but since SFCs support concurrency, so it may happen that after one transition two concurrent threads of execution will start. So that is why we have said steps following it are activated. and those preceding it are deactivated. Only transitions following active states. So, again when you are in a state already which is active, only certain transitions can occur. So, therefore, only those transitions need to be evaluated. So, only those are evaluated. A transition can also be it can either be a program itself having embodying very complicated logic, or it can be a simple variable like in our example, which is simple enough. So, for example, in this case it says that S1 is actually an initial step, and then if transition while S1 is active, T1 is active, and if the conditions for T1 are fulfilled, then it will come to S2. While at S2, if T2 will become also active, and if T2 occurs, then it will go to S3. So, you see that if you see the activations in scan 1, it may so happen that S1 and T1 are active, while in scan 2 it may happen that T1 has fired. Once T1 has fired, that is actually taken place, because T1 is active, so it has come to S2 and then T2 is active. So, if T2 is active, it is continuously evaluated. It may happen that in scan 3 T2 is evaluated to be false, so these two continue to be active, while at scan 4 it may happen that T2 is now actually become true. So, therefore, S3 has become active, and then any transition outgoing from it will become active. So, this is in this way certain parts of the program at a time becomes active as the system moves through the sequential function chart. For example, there are you can describe several kinds of programming constructs. For example, this is an I'm sorry. So, for example, this is a case where the system, if at S1 while the system is at S1, T1 and T2 are active. So, any one of them can become true, and if T1 is true, S2, the next active state will be S2. If T2 is true, the next active state will be S3. While it could conceivably also happen that T1 and T2 in a given scan, T1 and T2 both become active. So, in that case you have to resolve, because both transitions cannot take place simultaneously. So, you have to say that, so there is a convention that the leftmost transition takes place. So, if T1 and T2 will both become active at the same time, true at the same time, then T1 is assumed to have taken place. So, that was a selective or alternative branch, that is the system can either flow through this branch or flow through this branch, but not both of them simultaneously. So, as I said that if S1 is active, T1 is true, and then S2 becomes active. If T1 is false and T2 is true, then S3 becomes active, and then the moment S3 becomes active, S1 becomes inactive. Similarly, left to right priority, as I said, and only one branch can be active at a time. If S4 is active and T3 becomes true, S6 becomes active and S4 becomes inactive, same thing. Similarly, just like selective or alternative branches, you can also have simultaneous or parallel branches. So, this is a new construct which is not possible to be implemented in a normal state machine. So, this is a construct that helps concurrent control programs. The actual realization how you will run concurrent executions can be made using various operating system methodologies such as multitasking. So, here you have a parallel branch. So, when you see that at S1, if T1 occurs, then both these states become active together, and then at some point of time S4 becomes active, but T2 cannot take place unless this branch also comes to S5. So, only when S4 and S5 will become active, at that time T2 will become active and it will be evaluated. So, if it evaluates to true, then it will come to S6, and then S4 and S5 will become inactive. So, if that is the same thing is written here, if S1 is active and T1 becomes true, S2 and S3 become active and S1 becomes inactive. If S4 and S5 are active and T2 becomes true, then S6 becomes active and S4 and S5 inactive. Okay. Similarly, you can have, you know, among program control statements, you can have jumps. So, for example, you have a jump where after S1, S2, after T3, it will go back to S1. Similarly, you can have a jump inside the loop. You can jumping here, you can either come to S5 or you can come to S1. So, basically, you can execute this kind of program control statements using SFCs. So, in jump cycle, jump occurs after transitions, and jump into or out of parallel sequence is illegal, because you cannot jump out of one sequence when you are in parallel. You must enter them together in any parallel sequence. While you are executing the sequence, you may be in different states at different arms, but you must enter them together and you must leave them together. Similarly, last, you may have termination of a program. So, a step without a following transition. If you have a step out of which there is no transition, then it is a dead state, and once it is activated, it can only be deactivated by a special instruction called SFC reset. You can nest programming, you can nest a concurrent loop within a concurrent loop. So, here if T1 occurs, S2 and S3, then from S3 if T2 occurs, then simultaneously S2, S4 and S5 can become active. And if all of them are active, then T3 will take place and then S6. Similarly, you see here what is happening, this exactly the same thing is happening, that here you have a selective branch. So, you can have you can either go into S2 through T1 or go into S3 through T2. That is a selective branch. While you are in a selective branch, you can execute a parallel branch, and then if when S4 and S5 are both active, at that time if T2 evaluates to true, then you will come to a jump which will again take you to S1. So, such control flows you can specify. So, we have come to the end of the lesson. In this lesson, we have, what have we learned? We have learned the broad steps in the sequence control design, and these are very important. That first of all, identify the inputs and outputs, then very critically study the system behavior, look at the requirements for manual control, operator safety, faults, etc., and then try to formalize this description. So, first maybe write the operation in crisp steps in English, and then try to convert this description of steps into some sort of formalism. And we have, in this lecture, we have seen the formalism of sequential state machines, which can be programmed using a sequential function chart. So, this modeling, we have seen that how to model a particular application. We took a very simple industrial application like a stamping process and built its state machine, and then we have shown that how, given the state machine, how very mechanically you can arrive at a, how you can actually structure your program and then write the transition logic and the state logic and the output logic. And we have seen that this is very much expected to lead to error free programs. And finally, we actually found a syntax, some language, graphical language, which can actually capture this flow of logic in terms of states and transitions. So, this program control or the program flow description strategy using sequential function charts we have seen. So, now before ending, I think it is nice to look at some problems. So, for your examples, you can try to create. Let's look at exercise problem number 1. So, the problem number 1 says create an RLL program for traffic light control. So, what happens? That the lights should have crosswalk buttons for both direction of traffic lights. Okay. a normal light sequence for both directions will be green. A normal light sequence for both directions will be green 16 seconds and yellow 4 seconds. If the crosswalk button has been pushed, then a walk light will be on for 10 seconds. If the crosswalk button has been pushed, then a walk light will be on for 10 seconds and the green light will be extended to 24 seconds, right. So, this is, see, this much of description is only given. Now, so what is the task? The first task would be to develop a state machine description and probably write it in terms of an SFC, and then while going to do this SFC, we will actually encounter we can encounter several problems. For example, we may find that some things are not stated. For example, let us look at the SFC of this problem. So, we will, for the time being, we will skip problem number 2, or okay, let us look at problem number 2 next, and then we will go to the SFCs. So, the next problem says design a garage door controller using an SFC. So, the behavior of the garage door controller is like this. There is a single button in the garage and a single button remote control. When the button is pushed, the door will pushed once. When the button will be pushed once, then the door will move up or down. So, you push it once, it will move up or down. If the button is pushed once while moving, then the door will stop and a second push will start motion again in the opposite direction. So, you have a single button which you are going to push. So, you press it once, it might go up, press it again, it will stop, press it again, it will reverse. So, you have only one single button. So, you see that this is purely sequential behavior. So, unless you have a concept of state, you can never, you are actually pressing the same button, but sometimes it is stopping, sometimes it is moving up, sometimes it is moving down, and this kind of logic, it is not possible to model using only input output. Then you have to bring in the concept of memory or state, as you might have noticed when you have designed digital logic circuits. So, you have sequential, whenever you have memory, you have sequential logic. So, let us look at then there are top bottom limit switches to stop the motion of the door. Obviously, you have pressed a button, it is going up, it has to stop somewhere. So, you have to have limit switches. There is a light beam across the bottom of the door. If the beam is cut while the door is closing, then the door will stop and reverse. So, if you have, while the door is closing, suppose if you put something below it, then that is, you are trying to ensure that the door can actually close, because otherwise what will happen is that the door will get stuck. If you have kept anything there, suppose the back of your car is actually sticking out, then the door will go and hit your car. So, the door will close fully only if there is a light beam which is not interrupted, which means that there is clearance. Otherwise, if the light beam is interrupted at any time, immediately the door will stop and reverse. So, it will think that there is something, it cannot close it. There is a garage light that will be on for 5 minutes after the door opens or closes. So, you have a garage light which can be open for 5 minutes after the door opens or closes. So, you have to use a timer here. So any time you do an operation, the light is going to go on and stay 5 minutes. Okay. So, we have the two. Let us first look at the next one, which is simpler. So, here you have the garage door. So, let us see how they have modeled it. So, you have in this case, so if button is pressed, and so you have step 1 going to step 2 going to step 3. This is the closed door. So, if let us see, let us go back. So, there is a single button in the garage and a single button remote control. So, you can have either a button pressed in the garage or you can have a button pressed in from the remote, right. So, there are two kinds of buttons. So, you have either a button pressed from the garage or from the remote, then we will go to step 3 and it will start closing the door. This is the output. On the other hand, if button has been, so if from there, if either a button has been pressed either from local or from remote, or if, so if we press a button, what will happen? Then the door will stop. On the other hand, if the limit switch is made, what will happen? The door will stop. So, if either a button has been pressed or the bottom limit switch is reached, then immediately the door will stop. Or if the light beam is interrupted, then it will not only stop, it will actually reverse, right. So, immediately it is going to reverse. Here what happens is that if you have pressed a button and to stop it, then if you press it again, then it will go to reverse. So, this is a, you see, we have captured the behavior of the garage door in this form using SFC. So, you can do a similar thing also for the traffic light, that let that be an exercise. So, that brings us to the end of this lesson. Thank you very much and see you again for the next lesson. Bye bye. Welcome to lesson 22. So far we have learnt about the basic functioning of a PLC, we have learnt how to write a program for it, but all this time we have seen the PLC as an abstract device. We have not seen what is inside a PLC system, what actually physically makes it. So, in this lesson we are going to look at the hardware environment of the PLCs, basically what PLC systems are made of, right. So, we are going to look at components, we are going to look at components of the PLC system, their architecture, by which I mean that how they are organized, how they are connected, and their functionality, that is describing what they do. Okay. So, now let us see. Before we begin, it is customary to see the instructional objectives. So, the instructional objectives are the following. First, after going through this lesson, one should be able to mention the distinguishing features of industrial automation computational tasks. A PLC basically is a computer. So, it performs computational tasks related to industrial automation, but these tasks have certain very distinguishing features compared to the other tasks which are, let us say, done in an office environment. So, we are going to, you should be able to mention some of these features, mention major hardware components of a PLC, describe major typical functional features and performance specifications for the CPU, central processing unit, IO or input output, MMI, the man machine interface, and communication modules. Okay. Then explain the advantages of a function module. So, what are the advantages of a function module? You will be able to explain, and describe some major typical function module types. So, these are the instructional objectives. The program execution in these systems is very interesting. There are generally 3-4 different types of program execution modes specified. For example, a mode could be cyclic. By cyclic we mean that you have a number of computational tasks begin just like RLL program execution. So, begin here, come to the end, start all over again. So, this just goes on. Typically cycle time remains more or less constant, but it could vary a little bit depending on the program logic. For example, if you have some program control statements, if then else kind of statements, then whether some block will be executed or not will actually depend on the data. So, program execution time is not always constant, it actually depends on data, but roughly it will be constant, and in fact it is preferable that it is constant, so that you are not surprised that for some value of data suddenly your program execution takes a very long time and your deadlines are missed. So, it is preferred that real time programs have predictable and not too much varying time requirements. The advantages of distributed network IO are well understood: cost saving on maintaining integrity of high speed signals, because basically the advantages of digital communication, and the advantages of having an intelligent module near the machine. So, you can have good sensor diagnostics, fault can be much more, monitoring functions can be realized without overloading the CPU. You can do special functions like startup. So, in a sense, in such cases the PLC CPU really works like a supervisory system, and the actual controls is done on the spot. So, you have better centralized coordination and monitoring. So, we have come to the end of the lecture, and so we have, I hope you have got a fair idea about what makes a PLC system, and as is customary, again you have some points to ponder. So, think whether you can mention two distinguishing features of industrial automation tasks compared to, let us say, a task in a bank, which are also computational tasks which also communicate. Mention 5 major components of a PLC system. We have mentioned more than 5, so you should be able to mention 5, and distinguish between normal, distributed and networked IO. So, here we end today. Thank you very much. We will meet again.